Thank you, Manfred, for this kind invitation, and hello to all of you around the world. I'm really happy to give this presentation today. So now let's try to share my slides. Is this okay, Manfred? Do you see my slides, Manfred?
Yes, now it's perfect.
Yes, very good. Mm-hmm.
So, on the left-hand side, you see a great image of the village of Brienz, which was taken between May 8th and 12th of last year. This shows the evacuation of the village. And on the right-hand side, you see the failed slope, which failed on June 15th at night last year. So I will try to explain you how did it come to this situation, and how did we take the decisions, or how did we make the recommendations which we made during this period of time. So I first give you an introduction into the geologic predisposition and the kinematic models of this unstable compartment at Brienz. Then we will look into hazard scenarios of this Insel compartment, which are really the foundation for the development of an early warning model and the time to failure predictions. And then we look what has really happened in comparison to our predictions, what displacements, accelerations were observed, and how did it come to the collapse of June 15th. And then I give you some take-home messages, and close with a slide about acknowledgements, because what I show here today is the result of a big teamwork with many people and companies involved. So here you see the large-scale picture of the unstable area. On the left-hand side, you see the highest mountain in the area. It's called Piz Linard. It's about 3,000 meters high. And on the right-hand side, you see a river, the Albula River. And between Piz Linard and the Albula River, we have deep-seated gravitational slope deformations. And the Insel compartment, which failed on June 15th, is just a small section of this very large deep-seated slope deformation. I just show you a few geomorphological features. So when you're really at high elevation below Piz Linard, you see a lot of uphill-facing scarps. When you are in the mid-slope section, where we have the Insel compartment, you see a lot of fresh normal scarps dipping in the same direction like the slope. And when we go to the toe of this landslide, we have a lot of thrust sheets and secondary failures. This entire mountain slope deformation has been studied for very long periods of time. It was studied, for example, also by Heim at the beginning of the 20th century. And what you see here is a geologic tectonic cross-section for the entire deep-seated mountain slope deformation. And what you can see is that this slope is composed of really diverse geologic tectonic units. These tectonic units are thrust sheets, imbricates from the Penninic and the Austro-Alpine regions of the Alps. And I will go through some of these tectonic units in my next slide. What was studied in much greater detail is the lower sector of this mountain slope deformation, because here, where I show you now this red box, people observed active landslide deformations, let's say, during the last decades. And these active mountain slope deformations were bigger than, let's say, 10 centimeters per year in an area covering about 170 million cubic meter of active rock. And because these deformations, at least locally, increased during the last 10 years, this area was studied in great detail. Yeah, especially since about the year 2019, a series of deep double tube, triple tube cored boreholes have been drilled into this lower sector of these deep mountain slope deformation around the village of Brienz. So the village of Brienz is located on this flattened plateau, and here you see the village of Brienz on the map, and you see we have carried out a lot of deep, very expensive drillings in that area, and they were also supported by geophysical investigations, hybrid seismic lines, geoelectric investigations, hydrogeologic investigations. So we got a very detailed geologic, hydrogeologic, geotechnical understanding of the structures and the displacements in the lower sector of this mountain slope deformation. Now we look at the very recent geologic section through the center of what we call a landslide complex, and you will very soon see why we call this a landslide complex. This is a very complicated, I would say, geologic section. Now I show you some of the important tectonic units. So at the bottom, and this is very important, you have fleche. Yeah, fleche is succession of sandstones and marley interlayers, and fleche worldwide is a very important formation when you deal with landslides. On top of fleche, you have a similar formation, which is not so easy to distinguish in the field. It's called algae schist. It's also a sequence of finely bedded marl and, let's say, sandy limestones. And on top of these schists, we have much stronger formations. We first have Reibler schists, Reibler Raywacky, and dolomite rocks. And then on top, we have very hard dolomites of the Wallaccia formation. So this is the general geologic picture. What you can see now on this cross-section are different lines. Red lines are active sliding surfaces, and yellow lines are sliding surfaces which are not very active today, but which have been very important sliding surfaces in the geological past. So this active part, which we have studied in great detail, shows you that we deal with a very complex multi-stage landslide history. And when you look at this lowermost sector of the landslide, you can see that the fleche and algae schists have been thrusted over quaternary fluvial deposits of the Albula River, and that the total, thrusting distance here amounts to about 500 meters. We also found below the thrusting plane buried trees, and we dated these buried trees, and we can show that this active landslide in the frontal part has been active at least since the last 13,000 years. So this is the late glacial period. We can also see, when we map these units in greater detail, what types of mass wasting phenomena have occurred in the geologic past. And we see that we had compound slides in the past. We also see deposits from rock mass faults, and we also see deposits from dry granular flows. So it's a very complicated history of landslide activity around the area of Brienz. Also today, this active landslide mass is not just one single homogeneous sliding body. It can be differentiated into several active compartments, and some of these active compartments reactivate some of these old sliding surfaces. So this very thick basal sliding zone, which you see here, has not just formed in the last decade. Yeah, it was just reactivated during several of these past landslide events. The most important and the most active compartment during the last year, I would say, was the Insel compartment. And here you can now get an idea of where the Insel compartment is located. It's what we call a suspended rock slide with a compound rupture plane. What you see here in red is the current topography, in blue is the topography before the failure, and the rupture plane, in fact, goes at the deeper elevation, which is just, again, buried today below debris, at least in the frontal part. Now, we have monitored the Insel compartment, which is the main topic of today with diverse monitoring systems. What you see here is again a map view with the village of Brienz and the location of the Insel compartment. And here what I show you are permanent time-lapse cameras, and some of these images from these time-lapse cameras have been used to create displacement maps with digital image correlation analysis. So we have a camera looking from the west, a camera looking from the east, a camera looking from south to north, and a camera looking from north to south onto the Insel compartment. When we look at the image from this eastern camera onto the Insel compartment, we get this picture. So here you see again this suspended rock slide. You see the suspended rock slide includes
let's focus on one.
Dolomites from the Valacha formation in the central part, these complex units of the Ribler formation, and in the lower part, these relatively weak clay-rich schists of the Allgäu formation. The colors which you see here are displacement velocities in 2D in this plane calculated from digital image correlation. And this red line is just kind of a schematic estimated location of the basal rupture surface. Now this Insel compartment, which you see here so nicely, this is an image from May 19th of last year. Yeah. So this is more or less 1 month before this compartment collapsed. Did not look always like that. Yeah. So we also have ground-based interferometric radar. And here you see more or less the same area. Here is the Brienz village. And here is the future Insel compartment located. You see a velocity map. Velocity shown here, of course, is only along line of sight because this is a georadar looking more or less from south to north. And I always show you this velocity map with the same velocity scale, which goes much higher because this is an early image where the velocity was not so high. This is a velocity image from end of September 2020. So in September 2020, we didn't see, you know, an Insel compartment standing out in terms of velocity from the surrounding units. We saw some velocity hotspots. Yeah. 6 months later, you see that more or less the larger area around the future Insel compartment that shows increased velocity. You start to see a northeastern velocity discontinuity, so a boundary of a compartment. And this follows pre-existing steeply dipping faults. Now, 1 year later, we see that now the velocities of the future Insel compartment are remarkably higher than all the surrounding other compartments. We also start to see a northern boundary, yeah, a kind of a headscarp forming. And again, 1 year later, in February of last year, we more or less have the fully developed Insel compartment with clear velocity boundaries in the east, north and west. Here the boundary is not so sharp because we have a thick coverage with debris from rockfall events. So this is kind of the birth of an instability, yeah, of a compound rock slide. And this compound rock slide forms within a remarkably short period of time, considering that the total volume is about 1.5 million cubic meter of rock of this compartment. This is also reflected in geologic cross-sections. So this was an early geologic cross-section, more or less along the profile which you saw before. This was created in the year 2020. So when the Insel compartment was not at all fully developed, and people thought, well, this is a combination of toppling and sliding, mainly in the Wallacea dolomites, and sliding mainly occurs along bedding plains in the dolomite. This is a much more recent geologic section. It's not exactly at the same location. It doesn't matter. But here you see, you know, how this instability progressed towards the toe into the Allgäu schists, which are shown here in brown, and only through time a fully developed rupture and then sliding plane developed, which here is hypothesized to be a kind of a bilinear geometry. So this is just the representation of this evolution of the displacement field in terms of kinematics and cross-sections of the instability. So we knew there is an instability. We knew the instability was developing. So in end of February of last year, we had a fully developed unstable compartment, which was much faster than the surrounding parts of this landslide mass. And we had to look into the future and develop hazard scenarios for this Insel compartment. Now, hazard scenarios can involve just a further increase in velocity with the same type of mechanism, maybe a compound sliding. But what is even much more important, if you have to deal with hazard scenarios, it could also be that we have in the future changes of transport processes. And this is a diagram showing you, let's say, typical transport processes occurring in unstable geological masses. So this is just a diagram where on the horizontal axis you have time, and on the vertical axis you have displacement. So when you are in this yellow area, you have relatively small displacement in large time. So this is a very slow mass movement, extremely slow, maybe, possibly, yeah. And when you have a mass movement which follows a steep line, something will occur which is extremely rapid. And we know that landslide processes can change through time, and that a landslide which initially might have been a toppling instability can transition into a rotational, compound, or translational slide. And a compound slide could also transform into a granular flow or a rock avalanche or a big rock mass fall. So we considered these changes in transport processes, which could also occur at the location of the Insel compartment. And all these changes in transport processes normally are connected with dramatic accelerations. And in fact, we had such changes in processes. So initially, when you look at the first profile in 2020, it was mainly toppling, sliding instability, which then in 23, in February, became a compound sliding instability. And you will see when, in fact, this instability failed in June, it failed as a series of granular flows and rock mass falls. So we made such an assessment as in-depth as possible of these future scenarios and velocities. And for a rock slide, key factors controlling such process changes are the slide geometry, the stress conditions, are the slide mass internal shear strengths, especially when you think about a compound slide. It's not only the basal rupture plane shear strengths, which has a big control on the failure and post-failure velocity. What is also important are type, duration, and intensity of external loadings, which might affect the landslide velocity, dynamic behavior, or might also not affect strongly the landslide velocity behavior, and lateral restraints and toe buttressing. So, of course, a landslide, also the Insel landslide, is not a simple 2D problem. You also have lateral restraints like the faults, which I introduced before. And a landslide could also be buttressed at the toe by some kind of obstacle. So we looked into these key controlling factors very systematically for the Insel compartment. And from this analysis, and also comparing with what has happened in the past at this locality, we came up with these scenarios for the Insel compartment. 60% probability of occurrence in the next 5 years was assigned to a rock slide. Yeah, so we thought, well, most likely the rock slide, which had formed at the end of February 23, would just continue as a rock slide, maybe with some higher velocities. And we already observed, of course, at the beginning of the year 23, a lot of rockfall activity related to this Insel compartment, and we expected that just, things would continue as they had been in the past with a lot of rockfall activity. But we also had finally concluded that there could also be a process change, that this rock slide could transition into a granular flow, maybe related to a collapse of the rock slide. We gave this a 30% probability of occurrence, and we could not completely neglect, the possibility that this rock slide, which was, 1.5 million cubic meter in volume, could also transition into a rock avalanche. For certain reasons, we assumed that this scenario would have a very low probability, but still it had to be considered. Now, a rock avalanche, as I think all of you know, is a scenario with an extremely destructive potential. And here you see the conditional probabilities that certain areas below the Insel compartment would be damaged by a rock avalanche in the next 5 years. And you see here, this is now the conditional probability, assuming that 1.5 million cubic meter of rock would fail and form a rock avalanche. Then we would, with 90% probability, hit and damage the village of Brienz. And with a probability of about 30%, we would hit a very important railway line and a very important national road connection, to southern and eastern Switzerland. So this is the conditional probability. If you multiply this with the likelihood or probability of the occurrence of a rock avalanche, then these numbers are much smaller. Then you have maybe a 1% probability that you really damage the railway line at the toe of the slope close to the Albula River. But because this was the highest risk scenario, we had to deal with it. And we had to develop an early warning system, mainly avoiding this kind of scenario, even though the likelihood was very small. So what was our early warning model? What you see here is maybe, that kind of a hierarchical system, how we try to link our landslide model, which I have previously described, to do with a final political decision at the community level. And kind of in between the landslide model and the final decisions taken by the decision makers to evacuate, for example, the village or close the roads, is an early warning model. So this early warning model includes early warning parameters, velocity predictions, warning criteria, alarm levels, and recommendations which are made by the scientists to the decision-making stakeholders. Yeah? And at the core, and I really want to stress that, is the landslide model. So if your investigations of the landslide are poor, if you have a wrong understanding of the landslide, you will also come up with a wrong early warning model and wrong recommendations and decisions. So it's really essential that you carefully investigate the object which can generate these high risks. Here you see the actors. So one company and a lot of subcontractors of this company were responsible to develop the landslide model with external experts like me supporting them. The early warning model was developed and operated by another company and a series of other subcontractors, and again supported by an expert panel, which included Andreas Huwiller, for example, and myself. And the early warning expert panel finally, together with that company, made recommendations to the community, to the civil protection, the decision makers, which finally decided on what had to be done. So now I go more into the details of the early warning model. The early warning model needs early warning parameters. We distinguished primary, secondary, and tertiary early warning parameters. The primary parameters are instability, volume, velocity, and acceleration. Secondary parameters are rockfall activity, morphological observations, displacement vector orientations, and tertiary early warning parameters were weather-related forecasts mainly. Then we had to assess these early warning parameters with certain criteria. And one of the very important methods to assess the observed velocities and accelerations was a velocity model, which we have derived. And from this velocity model, we could develop so-called velocity thresholds, which were then linked to different alarm levels. We also looked into other things like spatial patterns and frequency of rockfall activity. And we also looked very carefully in conditions required for the formation of a very mobile, very rapid rock avalanche. So these were our 4 alarm levels, which were derived together with decision-making people. So we had a 30-day alarm, and this was related to preliminary community warning, a 15-day alarm related to the village of Brienz evacuation, a 7-day alarm, and a 2-day alarm, where these very distant traffic lines of the railway and the road would be closed. This was, this very unlikely event of a very far run-out rock avalanche reaching the bottom of the valley. What is important that we, as let's say the people of the early warning team, made recommendations, not the decisions. We made recommendations from the scientific point of view to the decision makers at the community level. And what is also very important, we always had to very carefully communicate it, not only the expected scenarios, but also their likelihoods and our uncertainties of what would happen in the future. So our velocity model was really key to develop velocity thresholds, and I have not enough time to go into the details of the velocity model. It is assumed that this instability would follow a 3-stage creep curve with an acceleration in the 3rd creep stage, leading possibly to a collapse or catastrophic failure. I don't go through all the details here. I mean, there are some assumptions, which have to be fulfilled that such a strain or a velocity evolution indeed happens at the given slope. These are the fundamental equations for the 3rd creep stage. of this model. These equations have been derived by Fukuzono and Voigt a very long time ago, and are very famous equations relating the velocity. So this is the time derivative of the displacement to the acceleration. This is the second derivative of the displacement with respect to the time. So according to this equation, the acceleration would be a power of the given velocity at the given point in time, and the exponent is alpha multiplied by a constant a. So this equation can also be used to derive an equation for the velocity, and then you add another variable in this equation. Besides big A and alpha, you then also have TF, which is the time to failure, yeah, and VF, which is the velocity at failure. But if you assume VF is just infinite velocity, then this equation becomes much more simple. So based on these equations, yeah, we derived our velocity threshold. So what you see here is the observed displacement for a total station reflector as a function of time between February of last year and June of last year. And the red line is this fitted curve. It's now the displacement, not the velocity, to the observed about 90-day velocity at the given point in time. And the predicted velocity becomes extremely steep at a certain point in time, and this is the expected time of failure. And when you then go 30 days back, you can see what would be the corresponding displacement or velocity, and from this we derived the 30-day velocity threshold, and we could do the same thing for a 15-day threshold or a 2-day threshold. I skipped this. Yeah, so this is the decision tree of the Insel compartment, which has now included these velocity thresholds. Yeah, so we have the 30-day velocity threshold, the 15-day and the 7-day threshold, and see which recommendations were made when these thresholds were reached. It is important to say that the recommendations were not only based on these velocities. Yeah. We also looked at all the other primary and secondary early warning criteria. And for the short-term predictions, we also looked really at the, for example, weather forecasts, which are the third type of early warning criteria, which you have seen before. And before looking at these velocity thresholds and making these recommendations, we had to be sure that we have the conditions which are required for a rock avalanche to form. Yeah, so we had to have unstable volume, which was a minimal volume for such a scenario. And we also had to be sure that our model, which assumes we are in the third stage of a tertiary creep, is a real third stage of tertiary creep evolution. Yeah? And this requires that you look into longer periods of time, that you are sure that you do not just look into an acceleration, which is, for example, controlled by seasonal recharge variations, which is just a change of boundary condition, and it's not the change in the real instability of your compartment. So what has been observed in terms of displacements, accelerations leading to this collapse? We have a huge number of monitoring systems recording surface displacements. We have permanent and periodic GPS stations, but they do not cover the Insel compartment, which is here. We have a lot of reflectors on the Insel compartment. They were often destroyed and had to be replaced. So we never had so many reflectors as what you see in this image at the given point in time. Sometimes we only had 3 reflectors. Sometimes we maybe had 6 reflectors on the instability. And then we have these images from the georadar, the ground-based synthetic aperture radar, giving us very nice displacements and velocity along line of sight, which of course is very useful, but not the same as 3D displacements from a reflector. So here you see the long-term velocity evolution of the Insel compartment since 2012. These are reflectors which survived very long. And you see initially during these first years, we had increasing velocities, decreasing velocities, not a clear tertiary creep acceleration. Possibly the tertiary creep acceleration started around the year 2018, because then you have more or less kind of maybe weather modulated or other processes modulated acceleration seen in many of these reflectors. But as you might remember from these images from the georadar, the Insel compartment itself as an independent structural unit only started to form in the late year 21 or 22. Yeah. Now we look into the year 23, because then a lot of things happened. Yeah. So this is the velocity, not the displacement, between February and May of last year. These are some reflectors which were just destroyed, which were sitting on local instabilities and not representing the entire 1.5 million cubic meter rock mass, which had to be replaced. So you see here this increase in velocity, so this acceleration, but you can also see that this increase in velocity is not uniform, does not follow the ideal, exponential curve of this Voigt model. You can also see that until April, for example, we had total cumulative displacements, which were already very high. So this is 40-meter cumulative displacement for this reflector and 60-meter cumulative displacement from this reflector sitting on the Insel compartment. And these are very high velocities, which we had already in April and May. These are 200 millimeter, 600 millimeter per day. So this is very unusual, for a strong rock mass to develop these high velocities over such long periods of time without failing. So we thought that this might be related to this relatively weak schists at the base of the Insel instability. Then in June, we had a further acceleration, which was so high that it cannot be plotted on this y-axis. So here you see the y-axis goes now up to 2.4 meter velocity per day. Yeah. And on the last day, we had an additional acceleration, which was very dramatic during the last hours before the Insel compartment collapsed. We had short-term velocities of up to 45 meter per day over a 6-hour monitoring interval. So this is a very unusual dynamic evolution of an instability, and a very tricky one, to forecast properly. I can't go now into this detail because time is running out. We use these velocity thresholds, but you must be aware that for every single observation point, and we fitted our model to every individual point, we got a different velocity threshold, for example, for the 30-day, 15-day, and 7-day. So we had to do some statistical processing of the data and consider this variability in our communication of uncertainty to the decision-making people. When we look at the stability of our velocity thresholds, we made a very astonishing and important observation. So this is a reflector number 715. And this is the 60-day velocity threshold, maybe around 30 millimeter per day. And you see that we repeated, these fits to the observed displacements every couple of days, that our velocity threshold for the 60-day threshold and for the 30-day threshold and for the 15-day threshold, they're very stable values. But this is not the case when you look at the short-term thresholds. You see that they vary by more than 100%. Yeah, and this was the case for all our observation points, for all our reflectors. So it became very clear that short-term velocity thresholds, as derived from Voigt's model, were not applicable. Yeah, so we had to take decisions on made short-term recommendation before the collapse without considering this velocity model. So this is what has happened. Yeah. So we recommended a community warning a few days before May 8th. We recommended a village evacuation on May 8th. And this was not 15 days before failure. This was about 1 month before failure, because we included the uncertainty in our model, yeah, or failure prediction. Then we recommended an entry ban also quite quickly. And the 2-day alarm threshold was recommended very late. Yeah, so this was just the road closure, the railway closure at the bottom of the valley was in fact recommended on the same day as when the slope collapsed. There are geological explanations why we had this complex velocity evolution. I cannot now really go into the details. It's really related to the complex geology with diverse, mechanical behaviors in the lower passive wedge and the upper active wedge of this instability. And we could also see that this hypothesis about, the factors controlling the velocity evolution might be verified by field observations. I skipped this part as well. And this is really what has happened. In the night of June 15th, it was very dark. So these are pictures taken on June 16th. So all our cameras were not extremely useful, but because we had a lot of other sensors, Doppler radar, georadar, seismic and acoustic sensors, in combination with mapping of these deposits, we could derive what had happened at night very reliably, I would say. Yeah. So around at 10 o'clock, we started to have a series of dry granular flows, mainly from the toe of the landslide, where we had these weak algal schists. And these dry granular flows could even be tracked on the georadar as relatively rapid events, also reaching quite far, but of course not comparable to a real rock avalanche. And then the foot of the instability, was released, and the relatively strong Wallacea dolomites, or at least part of the remaining Wallacea dolomites, collapsed as a rock mass fall event at around 1143. And this could also be seen as a very important seismic signal. These were observations which we did not have when we made our recommendations, especially for the short-term prediction. These were observations which were given to us on the following days, observation made by local population. And this is really also important that you see this. These are images taken from the other side of the valley, on the other side of the Albula River. This is how the Insel compartment looked on June the 2nd last year. And this is how the Insel compartment looked directly on the same day before the Insel compartment collapsed. And you can see here this dark band, which is a very fresh, very extended, fresh scarp. Yeah, this would have shown us that really a large volume was going to collapse, yeah, immediately. So these are these geomorphological features, which are, of course, also extremely important, but we didn't have geologists everywhere for all the time. And this main scarp, which really developed in the last day before the failure, could then also be seen on some of these cameras in retrospect. So take-home messages and acknowledgements. The Insel compartment developed from a minor instability to a 1.5 million cubic meter suspended rock slide within 2 to 3 years, which is really rapid. When the Insel compartment had been fully developed, and this also means had developed a through-going basal shear zone, and we think this was in February or March of last year, the velocity reached 40 millimeter per day. and accelerated further, yeah, leading to very high cumulative displacements of several tens of meters. And we think that these high velocities and displacements are connected, yeah, to plastic displacements along a basal shear zone in the soft algae schists. The landslide long-term dynamic behavior could be approximated quite well by Voigt's law. So it was really the right recommendation to evacuate the village on May 8th. But the short-term velocity fluctuations which we observed in May and June cannot be represented by this model. So the compartment failed on the, I would say, an unexpected additional dramatic acceleration on June 15th, which just took place within a very short period of time. We expected this to last longer. And we think that this final failure was controlled by damage and strength loss of the active wedge in the brittle Wallacea Dolomites. And yes, we think this is quite a good story. The predicted scenarios in early 23 were really the right scenarios and were confirmed by the Insel compartment evolution. So this is my last slide. This is, let's say, the core group of people discussing all the results, coming up with recommendations to the decision makers. These are from diverse organizations, and in the end, we had meetings nearly every day. Yeah, and we could, of course, only make these recommendations based on a huge amount of extremely high quality data, which were derived by a lot of important companies, which you can see here on the right-hand side. Thank you.
Thank you, Simon, for this very, very impressive presentation, for this insight